All right, welcome back, everybody. Glad to have you here on a Thursday evening. So, two things before we get started. So, the first is, unless you have made other arrangements with me, I am assuming that you will be writing on July 27th, the second exam. That's next Wednesday. It's a different day of the week because I have a conflict on Monday night. But I assume that everyone will be writing at the same times that they wrote the last exam. I'll start setting up the drop boxes and things probably tomorrow, maybe only by Monday. So if you haven't gotten in touch with me about any conflicts, I would ask that you do that before 5 p.m., hopefully before like noon on Friday, and then I'll have some time to accommodate you if you have some issues. The other thing is I've started to get some emails about the S-rate surveys, the ratings of teacher effectiveness. I think that it's really beneficial for me to get that feedback. So I've incorporated feedback from those kinds of surveys in the past. I think particularly because this is the first time that I've ever taught a class on this kind of 6-week schedule. I think it would be really helpful for me to get feedback from you if you have feedback that you'd like to share. So if you feel like that's something that you'd like to do, I'd strongly encourage you to do that because, again, it is, I think, beneficial for me. So, it's crazy because it feels like we only just started, right? But in this 6-week kind of schedule, then we're also almost finished. So after this class, there will be 4 classes left. We're a little bit ahead of what's in the syllabus because we did this. We talked about reheat and regeneration last class. So today we're going to introduce and go through internal combustion engines. Then next class, we're going to introduce natural gas power plants and how we use those. I think we'll probably then stop at that point and take some time for review for exam 2. And then we'll have some classes left. So I think 5B, if we can get through it all, we'll see if we can or not. But I think at least we will do aircraft propulsion. So we'll look at how turbojet engines work. And then we may also talk about heat pumps and refrigeration cycles. If not, we'll move some of that heat pump and refrigeration stuff to the beginning of week 6. And then we have two classes in week 6 that we haven't accounted for yet. So my plan was just to have those be open sessions. What I usually do in the 15-week course is we have somewhere between usually 3 and 4 classes where I just have students ask questions, right? So sometimes general questions, but often what I do as we go through these different cycles is I'll ask students to sort of scour the internet or the textbook, look for the most complicated version of these different cycle problems that they can find and give one to me. And then you'll kind of get to see me struggling through how to do one of these problems. So instead of me doing a problem that I've done a bunch of times because I've taught the class before and they're the same examples that I do semester to semester, that way you get to see, like, how would I deal with it if I was the person that opened up the test and said, like, oh, I haven't really seen a problem like this. How do I use this general solution method that we've been trying to learn and apply that to real life problems? So hopefully we'll get 1.5 or 2 of these evening sessions that are just problems like that. I think that it'll be exciting for me. You get to play Stump the Chump over here. So again, the harder the question is, I think the better it is for all of us. So now in those open question type problems, right? And hopefully even in the examples that we do in class here, examples that I've done before, you'll kind of hopefully start to see the similarities in how I approach the problem, right? Because I generally follow the same process, right? The same map, right? So the first thing that I do when I think about these cycle analysis problems, and we've only really talked about Rankine cycles so far, but we'll see as we go to these different thermodynamic cycles, it's always going to be kind of the same things that we're interested in. Usually what we're trying to drive towards by the end is how do I characterize how well the cycle is doing? So there's some big characterization parameter. Now, all of these major characterization parameters, although sometimes we call it a thermal efficiency, sometimes we call it a coefficient of performance, but it's always going to be what's the energy benefit of the cycle and what's divided by what's the energy cost of the cycle. Now, when I look at the cycle, all of these thermodynamic cycles are a series of processes that are either run in series or, like that Rankine regeneration cycle, in parallel. So I got to ask myself, are these different processes open processes where mass is flowing through a system, stuff we're doing now on the second midterm, right? Or are they closed processes like we did on the first midterm, right? Now, after I know that, then I'll ask myself to do conservation of mass, which is trivial for a closed system because what happens to the mass is it stays in the piston cylinder assembly, right? For an open system, sometimes there it's trivial too because we know if it's steady state with one inlet and one outlet, well, the mass flow rate in is equal to the mass flow rate out. Where it gets to be tricky, right, is in that Rankine regeneration problem, right, where I'm encouraging you to bring your colored pencils because then you're going to have a different mass flow rate at different inlet and outlet ports on different devices. Then, after I know what's going on with the mass, I'll say, okay, what goes on with the energy, right? How is energy conserved as I move through these processes, right? I got to do the first law, but the version of the first law I use will be different depending on whether or not it's an open or a closed system. And then sometimes I'll do a second law analysis if the problem asks me something like, is this process possible? That'll give me symbolic solutions, right? And to me, that's kind of the low-hanging fruit because that part is very similar for all of these different cycles, right? And then what often takes the most time is how do I go through and fix the states? How do I get numbers to put into these equations? And in order to do that, I need to remember what the fluid is. The fluid is going to be water or something like it, maybe a refrigerant, that goes back and forth across the vapor dome, so something that we're boiling and then condensing, or it's going to be an ideal gas like air. And depending on what the fluid is, we have different strategies for how we find changes in specific enthalpy, changes in specific internal energy, and changes in specific entropy, which are often the things we're trying to solve for based on our symbolic solutions for the first and second law. Then this is kind of the grunt work, right? We got to go through, we got to fix all the states, we keep information on these different tables, right? Sometimes we're going to look stuff up on tables, do some interpolation, but sometimes we have different equations, like if it's a subcooled liquid, maybe it's delta H is Cp times delta T, or if it's an ideal gas, that's true as well. Right? Then I'm going to take the numbers that I have, I'm going to put them into the symbolic solutions that I had for the first and second law. That'll let me find things like work or power, heat or heat rates, right? And then I'm finally going to put those numbers back into this characterization parameter, and that's going to let me say something like, how efficient is my nuclear power plant, right? And then sometimes I'll compare how efficient the real power plant is to how efficient the ideal version of the power plant is, right? By looking at that Carnot efficiency. Remember, that's related only to the hot and cold temperatures, right? Now, so this is kind of my roadmap for how to do cycle analysis problems, but part of the reason that I like having a consistent process is because I don't like to memorize things. And even this is probably a little too much, right? It's like 6 points with a bunch of subpoints and stuff. So really, I think for all of these cycles, there are 3 questions that I ask myself. The first is, how do I characterize the cycle? Right? That's kind of 2 questions because it's basically asking me what's the energy benefit and what's the energy cost. So if it's a heat engine like a Rankine cycle, the energy benefit is mechanical power, or W dot net, and the energy cost is the heat that we have to put into the cycle. The second question I ask myself is the system open or closed? Because that will let me start to develop my symbolic solutions that I need to solve the problem. And then the last of the big 3 questions that I ask myself is what's the fluid? Because if I know what the fluid is, that'll set out the rules that I have for fixing the states, for finding things like H and U and S and specific volume. And the neat thing is that for all the different cycles that we'll talk about, even though it's the same general process to solve the problems, the answers to these 3 questions, for each cycle we look at has different permutations of the answers to these 3 questions. Right? And we'll start to see that today because we're going to move away from Rankine cycles, right? And we're going to start to talk about internal combustion engines, or sometimes people call them ICE engines. So I had to refrain from putting up a picture of like Ice Ice Baby, Vanilla Ice, from when I was growing up here, right? And we'll see that even though there's a lot of differences in this particular cycle compared to a Rankine cycle, it's not totally different, right? If we think about those 3 questions, some of it's the same, right? So we're going to start to look at an internal combustion engine, but the first part of the lecture today is kind of just about engine terminology, right? Now, I'm always a little bit nervous about giving this lecture because I told you about the work that I do, right? I manipulate little droplets of fluid with electric fields, right? And I know that there are lots and lots of mechanical engineering students who went into mechanical engineering because they love automobiles. They love the beauty of an automobile engine. Maybe they started taking apart and putting automobile engines back together when they were like 8, right? So there's going to be a lot of people when I'm teaching this class who know a lot more about engines than me, right? And it's okay if you're in that camp. Feel free to correct me if I get things wrong. But it's okay if you're not in that camp too. We've talked about how mechanical engineering is this super diverse subject, right? It's a huge tent in mechanical engineering, right? So you can be somebody like me who manipulates little droplets of fluid with electric fields, right? Or you can be a materials engineer who's trying to make the next best steel, right? Or you can be an automotive engineer who's on the Formula team or on Hot Wheels who, is building cars from the ground up, right? And racing them on the weekends, right? So it's okay if this is the first time you've seen a cutaway of a 4-cylinder internal combustion engine, right? And this internal combustion engine, they have these cylinders, right? And we know from the first part of this class that inside these cylinders we can have, or these piston cylinder assemblies, we can have thermodynamic processes where we're sort of exchanging heat energy for work, right? And that's what the internal combustion engine is doing, right? Now, sometimes it's in a car that maybe you're driving back and forth to work, right? But sometimes it's in a big truck, right? And, maybe we're learning more about trucks than we ever wanted to know, as we can't get anything from anywhere with regularity these days, or at least it sort of feels that way, right? Because trucks bring pretty much everything that we use everywhere that we are, right? It's part of the supply chain, right? So when we think about it thermodynamically, what's the energy benefit of an automobile, right? And, automobiles, they replaced horses, which replaced, human power, right? So the reason that internal combustion engines are used for the most part is because they're producing mechanical power, right? You step down on the gas and the wheels turn, right? So you're getting that spinning shaft, which is turning the wheel, which is propelling your vehicle forward or backward, I guess, too, right? Right? So we're trying to develop power or work with this internal combustion engine. So in that way, it's kind of like a Rankine cycle, right? Because the energy benefit of a Rankine cycle was to develop power. Now this one, again, these days, everybody is talking about what the cost of an internal combustion engine is, right? And, you know, the biggest ongoing cost of an automobile, right, is the cost to fuel it up, right? So, you know, we put liquid gasoline into most automobiles, but not all automobiles these days, right? And we do that because inside an internal combustion engine, what we do is we burn that fuel in a controlled way, and that gives us heat, right? So just like a Rankine cycle, this internal combustion engine is doing this energy transaction that's trading heat that we get from burning a fossil fuel like a coal engine, right? And it's giving us mechanical work or power. So an internal combustion engine is still a heat engine. So when we think about our three big questions about cycles, the first one is, how do I characterize the cycle? An internal combustion engine is characterized in the same way as a Rankine cycle is, because it's a heat engine. So what we're trying to get is work or power. That's the energy benefit. And the energy cost is heat in or heat rate in, depending on whether we're talking about elapsed time or rate versions of these equations. So this part is just like a Rankine cycle. But when we talk about our three big questions, that's where the similarities end, right? So what's the difference between this internal combustion engine, right, which is this piston cylinder assembly that keeps going around and around and around, right, and this Rankine cycle where water keeps going around and around and around, but it's, you know, going through these phase changes, right? So the similarity here is that they're both heat engines, right? So we're doing that same energy transaction, turning heat into mechanical work. The first difference, and we'll see that for internal combustion engines, this isn't exactly true. This is the model we're going to use, or the cartoon of the internal combustion engine that we'll use to understand how it works. We'll assume that all the thermodynamic processes that are happening in this internal combustion engine, we'll assume that they're closed system processes, right? So that mass is not entering or leaving our system. Right? That's different than the Rankine cycle, because in the Rankine cycle is a bit like an assembly line, right? Oh, we're developing power. We do that in the turbine. But then we go to the condenser. That's where we lose our heat, right? Then we go to the pump. That's where we put work in. Then we go to the boiler. That's where we put heat in. And we just keep doing it over and over again. So in the internal combustion engines that we'll talk about, they do those same four processes, but they all happen in the same place. Right? So the way we're going to model this engine is as if it's a closed system, that there's air inside this piston cylinder assembly. No new air comes in, no new air goes out. We'll see that's not exactly true, but it helps us to be able to solve problems with a pencil and a paper. Right? The next question, right, so that would give us our symbolic solutions for things like work and heat, which we need for our thermal efficiency. The next question is, well, how do I get numbers to put into those symbolic solutions? So I need to know what the fluid is. For a Rankine cycle, it was usually water, although you could get lower power systems that are maybe using something like a refrigerant, something that's boiling and condensing. But for an internal combustion engine, and we'll see this isn't actually exactly true either, but the assumption that we're going to make is that this process, the working fluid, is air or some other ideal gas, but generally air. Right? So even though they're both heat engines, when we think about these three questions, This is as far away from a Rankine cycle you could get and still be a heat engine, right? Because it's still a heat engine, so we characterize it the same way. But the way we get symbolic solutions is different because we'll use a different version of the first law. And the way that we fix the states will be different because it's air instead of water. Right? So it's not completely different, but it's mostly different, right? Or partially different. Right? Even though it's doing the same job. So this is when we start to introduce terms, right? So this is my very crude drawing of a piston cylinder assembly, right? This is my PowerPoint art on full display over here, right? So I guess the first thing, right, is, this is the cylinder, this part here, and this is the piston. The piston is the part that goes up and down. I like this animation, so you're going to get to see this one a bunch. Right? So the piston, if we think about it moving up and down, its lowest position we call bottom dead center, right? Because you want your piston to be centered in your cylinder, right? And it's the bottom of the travel that it has, right? And the top position, the uppermost position of the piston is top dead center, right? Notice that top dead center isn't having the top part of the piston flush with the top part of the cylinder, that there's some clearance between top dead center and the very top of our cylinder. Right? Now, the distance of travel, right? So the space between top dead center and bottom dead center, that length we call the stroke or the stroke length. Right? So sometimes people will talk about two-stroke and four-stroke engines, right? That means that to do a whole cycle, there's two strokes going up and going down, or there's four strokes up, down, up, down. Right? And don't worry if you don't get that yet. We'll talk about it a little bit. Right? So the stroke or stroke length is the length between bottom dead center and top dead center. So we'll notice that this describes a volume. Right? Now we call this the displacement volume. So this cylinder, right, it's circular in cross section. So, this volume, this displacement volume is a cylinder. And if, let's say, your exhaust valve, because there's a valve here, if that exhaust valve is open and you pushed your cylinder or your piston up from bottom dead center to top dead center, this displacement volume is the volume of air that you would push out of your cylinder, right? That's the equivalent of the internal combustion engine breathing out, right? It's, right? Like it's getting rid of in that case, it'll be this kind of spent air fuel mixture that's inside the piston cylinder assembly, right? But you got to notice that just like top dead center, because top dead center is not flush with the top of the cylinder, there's some volume here that's not displaced, that doesn't get pushed out of our piston cylinder assembly. So the displacement volume is not the entire volume at bottom dead center, right? It's the volume that's described by the stroke length and the diameter of the piston, or the cross-sectional area of the piston. So there's another common thing. So if you read about engines, right, one of the things that you might see as a parameter is something called the compression ratio, right? So again, I like that animation, right? So the compression ratio, it's funny because by the name, you might think it's got something to do with pressures, but it doesn't. The compression ratio is a ratio of volumes, right? And it's always bigger than 1. So the compression ratio is the volume in the piston cylinder assembly when you're at bottom dead center. That's the biggest volume in the system, divided by the volume in the piston cylinder assembly when you're at top dead center. That's the smallest amount of volume, right? So this is the largest volume ratio you could have inside your piston cylinder assembly. The number is always bigger than 1. right? All the volume ratios we're going to talk about are always bigger than 1. Another thing that's important here is engine speed. Now, I know that manual transmissions are kind of a dying breed, right? And again, as a mechanical engineer, it hurts me to admit this, but I've never owned a car with a manual transmission, right? But if you look, it's really important to pay attention to what your engine speed is when you're changing gears manually, right? But it's kind of weird because engine speed it's not about the speed, how fast the piston is moving up and down, although it's kind of related to that, right? It's registered in RPM when you look at it on your instrument cluster, right? Because what happens is this piston, there's like a 4-bar linkage that's connected here to a shaft that's spinning, and it's the rotational speed of that shaft that's telling you how fast your engine is going, right? Because the piston, as it moves up and down, right, you know, it has 0 velocity when it's at the top and the bottom and some velocity in between. So instead, we talk about the angular velocity of the shaft that's driving this whole motion, right? Now, because the units here are in rotations per minute, and if we're using the metric system, we might want something like radians per second. We're going to need to know how to do some unit conversion. So usually when we talk about RPM, we use the capital letter N, but if we're talking about radians per second, then we'll use the Greek letter omega, right? So there you take your rotations per minute, you multiply by 1 minute over 60 seconds, which gives you rotations per second. But then you know that there are 2 pi radians for every rotation, so this will give you your engine speed in radians per second. And remember, when we're multiplying out units, radians is kind of a unit that just sort of disappears, right? It's not really, you know, it kind of goes away into the ether, right? It's almost like it's dimensionless, right? Because it really is, well, I guess only if you divide by 2 pi. So never mind. So you cancel out the minutes here, you cancel out the rotations here, right? And you're going to get radians per second, right? Which is often in the metric system what we want an angular velocity to be measured in, right? So that's one thing, you know, it's an important parameter when you're driving your vehicle. It's maybe not as important as the speedometer, right? Because that's the one that determines whether or not you get a ticket. But, you know, knowing your engine speed can be important, right? Now, depending on what your vehicle looks like, it might not even be a vehicle. You could have a 2-stroke engine or a 4-stroke engine, right? Remember we talked about stroke length, right? Here you can see that the shaft, when we talk about rotations per minute, we're talking about how fast this shaft here is spinning, right? That tells us this rotational speed, and because this is a 4-bar, or what's it called? Because it's a simple machine with a 4-bar. What did I just call it? A 4-bar mechanism? No, I can't even remember. I tell you, sometimes, you know, this is what I talk about. We brought in a speaker once. I don't know if I've told you this story yet, but sometimes this is easier to describe when you're, you know, up at the board. But sometimes you feel like when you're standing at the board or you're giving a presentation, you're kind of in the zone of stupid because your brain just stops working every once in a while, right? So this is a 4-bar linkage, right? And it's moving around, right? And this is kind of like a simple machine, a mechanical machine, right? Now, depending on the type of application your engine needs, it can be a 2-stroke engine or a 4-stroke engine, right? So 2-stroke engines are usually kind of dirtier machines, but it's kind of a cheaper kind of engine. So if you have a dirt bike, right, or if you have like a gas-powered weed whacker or something, right, that's probably a 2-stroke engine. So it's going to go through an entirety of a thermodynamic cycle, which is like when we think about the Rankine cycle. So it you know, it produces power, it loses heat, it puts power in, and it gains heat. That's like the whole cycle. This does that same thing, but in only 2 strokes of the piston, right, instead of 4, right? But as your engine gets bigger, right? So this is like now you got a motorcycle, or if you're driving like, you know, I have a 4-cylinder Toyota Venza, right? I used to have a Toyota Corolla, right? They last forever. That's why I bought those cars. But although, you know, the Venza, it's like a station wagon, right? But you don't call it a station wagon anymore because that's not cool. But I'm starting to get rust on the bottom. My car's like 11 years old, and it's like on the bottom of the lift gate. So I gotta get somebody to grind that out, right? But these, you know, as your power requirements get bigger, then you start to move into a 4-stroke engine, which is a more complicated machine, generally more expensive to build, but generally runs cleaner for you know, these higher power applications. Another way that we can characterize internal combustion engines is how we get the combustion, right? How are we burning the fuel? So in my, you know, 4-cylinder Toyota engines, right, there are spark plugs, right? So what happens is, as there's this air-fuel mixture inside the piston cylinder assembly, and as that piston goes up, right, the pressure's going up, which means the temperature is going up, right, because PV is equal to MRT, right? But I got to start the fuel to burn because I want the fuel to burn because that increases the temperature more, increases the pressure more, and makes that gas that's in the system want to push that piston down, which in turn is what's spinning that shaft, right? So we can have spark ignition, right? So spark ignition engines are usually used for lower power applications, right? Or lighter weight vehicles, right? So this is something like if you're driving a car, you know, just a normal sort of vehicle in North America, probably it's a spark ignition engine. And you'll know because otherwise you've got to use a different pump, right? So if you're putting, you know, normal gas in your engine, it's a spark ignition engine, right? My John Deere lawnmower is also a spark ignition engine, and every once in a while I change the spark plugs, right? But there's another kind of ignition, right, that we call compression ignition, right? So still we have this air fuel mixture that's inside our piston cylinder assembly, but now we're going to compress this gas enough as the pressure is going up, the temperature is going up as well, and now I don't have to put that spark in to get the fuel to burn because the temperature of the gas, just by compressing it, gets hot enough that the fuel starts to burn. And again, when the fuel starts to burn, the temperature gets higher, the pressure gets higher, and then I start pushing this piston down, right? So here we tend to get better fuel efficiency at high power requirements when we're using compression ignition, but you got to use a different fuel like diesel fuel, right? So this in North America, if you're not talking about, you know, something that uses compressed natural gas, or, you know, we're starting to move to electric now too, right? But usually heavy buses or heavy trucks or buses, trains, a lot of ships, right? And if you have a diesel generator, because you know, the power in Rochester is sometimes touch and go, so sometimes you need a generator to keep your fridge going if you lose power for a significant amount of time. These things often run on compression ignition. So remember the first third of the class, right? When we were doing closed systems, and I said, oh, it's really nice when we draw PV diagrams, pressure versus volume diagrams, because we know that physically, if I could take the area under the curve in a pressure volume diagram, then I can get the work, right? This is what a PV diagram for an internal combustion engine might look like. Right? And remember at the beginning I said, well, we make a lot of assumptions like it's always closed or it's always air. And part of the reason we make a lot of assumptions is because solving this would be really hard with pen and paper, right? So we're going to talk about, just like we did, like what engineers do is, right, we try to make things better using imperfect information, right, or cartoons of how the universe really works, right? But here we'll talk about how a 4-stroke engine might run as it goes through a thermodynamic cycle, right? So we can think about the piston was at top dead center and now it's moving down to bottom dead center, right? So now we have, see, there's two valves here. This one on the left, this is my intake valve. This one on the right is my exhaust valve, right? So at first, when my piston is moving down, I have my intake valve open, right? So that means on my PV diagram, well, first, so that means because that valve is open and the volume is increasing, it means I'm bringing air in. I'm sucking air into the system, right? The pressure stays about constant, and because I'm increasing the volume, I'm bringing more air into the system, right? So that's kind of the first stroke in this 4-stroke cycle. Remember, a stroke is any time I go from top dead center to bottom dead center, or from bottom dead center to top dead center, right? So that's our first stroke, is the intake stroke. That's like breathing in, right? But then we get to this point where the intake valve closes. Now this is a closed system, right? And because as I turn my shaft around, the piston goes, first it comes down, but eventually it's going to get to a point where it moves back up, right? So then what happens in my second stroke, where both valves are now closed, is we have this compression stroke. So now what's happening is the volume's getting smaller, right? Because I'm moving from bottom dead center up to top dead center, but there's nowhere for the air to go because I closed both of these valves. What that means is my pressure goes up because I'm taking the same amount of air molecules and I'm packing them into a smaller space, right? Here, we don't, in real life, just have air. We have this air-fuel mixture, right? We're getting up as we're compressing. Not only is the pressure going up, but the temperature is going up too, right? And then we get to this sort of magic spot where, if it's a spark ignition engine, right, where that spark plug goes off, right? And now we get this rapid burn of the fuel in the air-fuel mixture, right? And that drives that temperature up, drives the pressure up, right? And that air, because the pressure is high, that means there's this big force on the piston that wants it to go down, right? So that drives the piston down. Now this is our third stroke. This is the equivalent of the turbine inside the Rankine cycle. This is the whole reason that we're running the internal combustion engine, to get to this stroke. This is the power stroke, right? This is where we're getting that mechanical power out. The whole rest of the cycle is just to get to this moment, right? So that we can drive that piston face down, produce force, and that's what's turning this shaft, right? And that, ultimately it's doing a lot of things in your vehicle, but one of those things is making the wheels turn, right? But now, once we get back to bottom dead center again, because we burned the fuel in our air-fuel mixture, we converted some oxygen and some hydrocarbon fuel, right, into carbon dioxide, probably some carbon monoxide, hopefully not that much, maybe some nitrous oxides in there too, again, hopefully not that much, but we consumed some oxygen, right? So we can't just keep running this with the same mass that's in the cylinder, because things don't burn when there's no oxygen, right? So we need fresh oxygen, right? Just like our bodies, right? We're breathing out more carbon dioxide than we breathe in, right? So the engine has to breathe out as well, right? So this last stroke, our exhaust stroke, we're at bottom dead center, right? The biggest volume. We open up our exhaust valve, and now that piston moves up, and as it moves up, because the exhaust valve is open, the pressure stays approximately constant because now there's some place for the air to go. We get rid of that exhaust gas, right? It goes out your tailpipe, right? Before we start everything again, right? So now with that exhaust valve open and the piston moving out, we're moving up, we're pushing out this spent air fuel mixture so that we can get back to where we started, right? And then what would happen is after this exhaust valve closes, then the intake valve opens, the piston moves down again, and we breathe fresh air back into the engine, and we just keep going around and around and around, right? And that's how a 4-stroke internal combustion engine works. Right? And the neat thing about something like this cutaway is a 4-cylinder engine. Right? These cylinders are in line. Sometimes they'll talk about, especially as you get to things, more cylinders, right? Like a 6-cylinder engine, they'll talk about a V6. So the pistons aren't in line, but they're in a V shape, right? But here they're in line. And even though these two pistons are at the same place and these two pistons are at the same place, each cylinder here is in a different stroke, right? So, one of them is doing intake, one of them is doing exhaust, one of them is doing power, and one of them is doing compression, right? So there's always one of the pistons is always pushing down, causing the shaft to rotate. And as that shaft rotates, one of the things it's doing is compressing the air in another cylinder, right? Or just moving the pistons up and down so you can breathe fresh air in and expel exhaust gas. Now, hopefully from this discussion, you get the idea that this is a pretty complicated thermodynamic cycle, right? If you were going to try to solve this thing without making a whole bunch of assumptions, I don't think you could do it with a pencil and paper. Certainly not in kind of the half hour that we sort of give you for an exam problem, right? The cycle, it's not adiabatic. Heat transfer is important here, right? There's combustion, which we don't talk about chemical reactions in this class, right? Because there's combustion, that means that the actual composition of the gas is changing. So if you were thinking about it from an ideal gas law perspective, the specific gas constant of the gas is changing because it's a different gas, right? Or a different composition of gases. Kinetic energy can be important here, even though we often neglect kinetic energy in our analyses so far. It's not at steady state. It's transient, right? So the piston is always moving up and down. Things are changing with time. Sometimes it's an open system, which means we would sometimes use some version of the first law. And other times it's a closed system. When both of those valves are closed, then it's a closed system, and we'd use a different version of the first law for that. So in order to get to a place where we can understand what's going on with these engines, we're going to have to make a lot of assumptions. Right? And remember that each assumption kind of brings us more into a cartoon than real life, but that doesn't mean that it's not useful, that we can't make something or make something better, even though the models are more simplistic than the real universe. Right? So we'll often do what we call an air standard analysis. Right? So that sort of is a broad term that encompasses a whole bunch of assumptions that we're going to make here. So we're going to neglect combustion. We're going to pretend that inside the cylinder is not this air-fuel mixture that, sometimes is unspent, sometimes is spent, sometimes is going through the process of burning the fuel. We're going to assume that the system is always closed. Right? So instead of combustion, we're just going to talk about, there's going to be some heat coming in and some heat going out. We're going to say that the system is always closed. Remember that means that delta E is equal to Q minus W instead of dE by dt is equal to a whole bunch of stuff. Right? We're going to say that all processes are ideal inside the engine, right? That it's reversible, a totally reversible process. Obviously, this is not the case, but it still helps us to get to usable information. This sort of goes with the fact that we're neglecting combustion, but we're going to assume that the working fluid is always just air that there's never any fuel in it, whether it's combusted or not, right? And then sometimes we'll even go one step further and assume that the specific heat of this gas is constant. Remember, we talked about when the answer to the question what's the fluid is, oh, it's air. That means that I have to say, oh, am I going to do constant specific heat or variable specific heat, right? So in this case, we could do constant specific heat, and then we sometimes call that a cold air standard analysis, because we're sort of neglecting how the temperature change changes that specific heat value, right? So because of this, we can't necessarily have a lot of trust in the number that we get, right? But it's still going to tell us some really important things about what happens to the power or the efficiency of the engine if I do something like change the compression ratio, right? Remember, the compression ratio was the biggest volume divided by the smallest volume, or the volume at bottom dead center divided by the volume at top dead center. So we can still get some qualitative information about how to change the performance even by using this analysis, which is relatively simple, right? Remember, simple doesn't mean easy, just means less complicated than the real thing, right? Another way that we can characterize an engine is by talking about its mean effective pressure. So remember how in the first third of the class we talked about how for closed systems work can be calculated as the integral of PdV, but if the pressure was constant, then you'd pull it out and you'd get work is equal to some constant pressure times the change in volume. So this is kind of where this idea for mean effective pressure comes from. You get the net work of one cycle in your system, and you divide it by your displacement volume, which again is the volume at bottom dead center minus the volume at top dead center, right? This is, I mean, I guess the engine is probably at this pressure at some point, but it's not really supposed to represent some physical pressure inside the engine, right? It's just some way of comparing two different engines. So you know that if you have the same engine speed, but your engine has a higher mean effective pressure, that means you're going to get more net work or more power out of your engine, right? And if you're running at the same, right? So that's what I was saying. So if you're running at the same engine speed, then more mean effective pressure means more work or more power. And if you have two engines with the same volume, if you have a bigger mean effective pressure, then you get higher work out of that engine as well, right? So still, when we talk about heat engines, which is an internal combustion engine is a heat engine, right? The way we characterize this, our first big question, sometimes the most important question, how do I characterize the cycle? Oh, because it's a heat engine, we talk about thermal efficiency, and it's always, though, energy benefit over energy cost. The energy benefit is work. The energy cost is heat in, right? Or it's net power over heat rate in, right? And I can think of the net power as the heat rate in minus the heat rate out, or I can think about the net work as heat in minus heat out, right? So how do I go about finding work and heat? Right? And the answer is, as is so often the case in thermodynamics, use the first law, right? But because the system is closed, right, that's one of the assumptions that we're making when we're running these internal combustion engine cycles, is that the system is always closed. That means I'm back to this picture of the universe, right, where the change in the energy in the system, or after I make some assumptions about kinetic and potential energy, the change in the internal energy in the system is equal to the heat that comes in minus the work that goes out, right? And if this was the first third of the class, I would tell you that, oh, we get heat using the first law, we get work by integrating PdV, And we get delta U by looking stuff up in the textbook. Right? Thermal efficiency can be, because it's closed systems, we're not often talking about powers and heat rates. We're back to talking about works and heats. Right? I can talk about work out plus work in. Remember, work out is positive, work in is negative. Divided by heat in. Or I can divide all those things by mass. Right? And I can get the lowercase version of those variables. Right? We'll talk about how to get powers and heat rates. And I can use those same equations. Right? So how do I find work and heat? The nice thing is, at least for one of the internal combustion engine cycles that we'll talk about, we can assume that most of the processes are simple systems. Right? Remember, simple doesn't mean easy, it means less complicated. And in a simple system or a simple process, thermodynamically, it means we either have heat or work, but not both. Right? So if the process is adiabatic, then I can cancel out my heat transfer term, right? And I'll get that work is the change in the internal energy, or work over mass is the change in the specific internal energy. Or if I'm going to say that a process is passive, one where I'm assuming that there's heat transfer happening, right, but not work, right, then heat transfer is equal to, again, delta big U, but notice that the order switched because Q is positive and it's minus W in this equation. Right? So I have U at the end minus U at the beginning. Okay. Now we get to this point when I have these equations where I gotta ask myself, what's the fluid? Right? Because now I need numbers for delta U. Right? And the fluid, when we're talking about internal combustion engines, is going to be air, or I guess some other ideal gas, but I mean, you're driving your car around in air, so the intake is air and the exhaust is mostly air. So that opens up for us the ideal gas law. Sometimes, particularly if we're trying to find mass, we're going to have to use pressure times volume is equal to mass times the specific gas constant, which remember is the universal gas constant divided by the molar mass, times the temperature, not a delta T, so that's Kelvin or Rankine, right? If I'm trying to find the mass, I'm stuck using that equation. Right? And remember, the units are kind of going to be tricky when I do that. But if I'm moving between states, I will often prefer to use PV over T at state 1 is equal to M times R, but it's a closed system, so the mass is constant, and I assume that there's no combustion, right? And then it's always just air, so the specific gas constant stays the same. So PV over T at state 1 is going to be equal to PV over T at state 2. Again, remember those temperatures have to be absolute temperatures. Really, anytime you're dealing with an ideal gas law problem, just reflexively turn those temperatures into Kelvin or Rankine. All right, so we can use the ideal gas law more than once in a given problem. But that doesn't help us because U, right, the specific internal energy, is not in the ideal gas equation, right? So we're going to have to find U or delta U, right? So we need to know whether we're going to assume a process has variable specific heat or constant specific heat. Right, so if it's variable specific heat, delta U actually is going to stay as delta U, and I have to find the individual specific internal energy values. Right, those are going to be a function of temperature, or as we'll see, maybe a function of the reduced volume. Right, I get these values from table A22. Right, if it's constant specific heat, I'll never actually find the individual specific internal energies, which is fine because I don't really care what they are, because I'm modeling, I'm going to assume that delta U is equal to CV times delta T. And the first law only ever really cares about the change in internal energy or specific internal energy. Now, it gets to be important for, this is going to be true for any cycle where the working fluid is an ideal gas. We need to know which one of our processes are isentropic. Those are going to be the ones where there's no heat transfer and it's ideal. Right? And the nice thing about the ideal or the internal combustion engine problems is every process is ideal. So we're really just looking for ones where there's no heat transfer and only work. Right? Those are going to be isentropic. Now, we talked a little bit about using variable specific heat to fix the states, that I only need one piece of information on that table, right? And we'll do an example like this today. But if I can find a VR value or a T value, then I can fix the state, right? So the ratio of volumes is going to be equal to the ratio of this VR value that's on that table A22. But if it's constant specific heat, and it's isentropic. When it's isentropic and constant specific heat, I'm looking for some equation that has K in the exponent. But you'll notice for both of these isentropic relationships, we're using the relationships that have volumes in it. And that's because these are closed systems. And in closed systems, we typically know volume ratios. So we're going to want to know what the volume ratios are. So that compression ratio we talked about is important. So I'm just going to pull this in here, right? This is the equation sheet that I made for the exam. I think it's good to have this on hand, even if you make your own, right? I think that I tried to organize this in a good way. Here's all the ideal gas law stuff that you need, right? And then there's even a separate part, isentropic ideal gas equations. Oftentimes, when you have one of these air cycle problems, you might get stuck fixing the next state and then look for the ones that are isentropic and then pick the right equation here, right? For internal combustion engines, because they're closed, we're going to look for ones with volume ratios. And then always for variable specific heat problems, I'm looking for VR or PR if I have pressure ratios, right? And for constant specific heat problems, I'm looking for some equation that has K in the exponent. Right, so I like the equation sheet that I made. I think you can still make your own equation sheet, but bring mine too. Right? So there's three different ways we're going to model internal combustion engines. Well, really only two, because we don't really do dual cycles. And the difference between an Otto cycle, which we'll learn first, I think it's the less complicated version, and then the diesel cycle, which we'll learn second, which is more complicated. We'll try to do both today, right? Is the assumption that we make when we're adding heat is different, right? So an Otto cycle is more like a spark ignition engine. We're going to assume that when we add heat, it happens almost instantaneously, so fast that the volume doesn't change, right? So Otto cycles happen at constant volume. Diesel cycles, the assumption that we make when we're adding heat is that they happen at constant pressure. And we'll see that makes it a little bit harder to solve diesel problems, right? And then in the textbook, it talks about dual cycle problems. So this is a more complicated, which probably means more realistic. Usually as you increase complexity, you get closer to the real life application. Here we assume that the heat addition process can be broken down into two parts, one part that's constant volume and one part that's constant pressure. Right? But we're going to focus on Otto and diesel cycles for the remainder of the day, and that's what we'll talk about for internal combustion engines. Right? There's one last thing. You might want to try to find the power of your engine, right? Because you might want to talk about how much horsepower your engine delivers, right? This is often sort of the marquee thing that they talk about when you're talking about a different engine that's in a particular vehicle, right? Now, here we know the work per cycle, right? And to get to power, we need some element of time. So we're going to need to know what I'm using here as capital omega, which is going to be how many cycles, how many thermodynamic cycles do we run per second, right? So if the work per cycle is joules per cycle, And capital omega is cycles per second. The cycles will cancel, and we'll get joules per second, which is watts, right? And we can convert watts to horsepower. If you want to do that, right, at the bottom of the equation sheet, useful constants and conversions, right? If you want to know what 1 horsepower is, right, if you have an answer in watts or kilowatts, you would just change it into watts. Or if you have BTU per minute, you can get that too, right? So there's some conversions on the equation sheet that I give. Again, I think the equation sheet that I've given you is enough, right? If we were doing it in person, that's the only equation sheet you would have. But because it's open exams, you can bring whatever information you want. But I would say have my equation sheet in there, because I won't ask you something that I don't think you could solve without that equation sheet. Somewhere over here. Yeah, here we go. Right, same thing if I wanted the heat rate, I would find heat per cycle multiplied by cycles per second, and that would give me joules per cycle. Right? But how do I change engine speed, which is in rotations per minute, into this cycles per second value? Right, so the thing that I need to know is not just the engine speed, but I need to know if it's a 2-stroke or a 4-stroke engine. Because what happens is for every rotation of our crankshaft here, we get 2 strokes, right? That if we started at bottom dead center, then the first half rotation would get us to top dead center, and the second half rotation would get us back to bottom dead center. So we're back to the same position in the same phase, right? Not thermodynamically, but phase meaning same direction, right? So a 4-stroke engine, to get 4 strokes to go up, down, I need 2 rotations per cycle, right? So if I'm trying to find out how many cycles per second that I have in a 4-stroke engine, I have to take my rotations per minute. I could turn that into, rotations per second. And then I have to divide the number of cycles I have by 2 rotations, because it takes 2 full rotations to get 1 cycle in a 4-stroke engine. Because to go 4 strokes, I need 2 rotations of that crankshaft. Right? In a 2-stroke engine, I do the whole cycle in only 2 strokes. So I only need 1 rotation. So my rotations per minute are also my cycles per minute. So if I just multiply by 1 minute per 60 seconds, then I get my cycles per second. Right? So it's important when you're trying to get to power, you're going to need your rotations per minute, but you have to know, is it a 4-stroke engine or a 2-stroke engine? It's obviously, maybe not obviously, right? But as the same with every other thing, it's a little more complicated if you want your power in imperial units, because nothing's ever an easy conversion, right? Because like you saw on that equation sheet, 1 horsepower is a nice round number like 42.4 BTU per minute, right? So when you find delta U in your textbook, it's going to be in BTU per kilogram, right? You multiply by the mass, you get BTU, right? But then you're going to have some kind of rotations per minute, right? So you'll have BTU per minute, right? So now you know that 1 horsepower is 42.4 BTU per minute, right? So it's important to know that conversion factor, which is on the equation sheet. But again, it's also important to know you need to know whether it's a 4-stroke engine, so it needs 2 rotations per cycle, or is it a 2-stroke engine where it's 1 rotation per cycle. We can go through this too. So for the second law, right, remember in an open system, it's Q dot over T plus the sum of M dot in, S in minus the sum of M dot out, S out plus sigma dot. For closed systems, we'll talk about elapsed format. So we get rid of the dots. That ds by dt just becomes delta S, right, or mass times the change in specific entropy. And the mass flow rates in or mass flow rates out, those terms go away, because it's a closed system. There is no mass coming in and there is no mass going out. right? But here, because the reason we need to know this, and you actually don't really need to do this analysis, right? But because when we have reversible processes, the entropy generation is always 0, right? So that means when I have a process that has no heat transfer, this term is 0, right? So if there's heat transfer, delta S is not 0, right? But if there's no heat transfer, delta S must be 0 because everything on the other side of the equation is 0, right? So I'm looking for the processes where there's no heat transfer. Here, that's going to be process 1 to 2 is compression, 3 to 4 is expansion or the power stroke. Right? That's the isentropic processes. And the isentropic processes are the key to fixing the states. Right? So for constant specific heat, right, we have these equations for S and delta S, but I don't really need those. But if I wanted from here to derive equations, right, for when delta S is equal to 0, which is going to be the important part, the equations I would get would be the ones in this table, right? So if it's constant specific heat and it's an internal combustion engine where I have volume ratios and it's the power stroke or the compression stroke where it's isentropic, this is the expression that I want. The volume ratio with K in the exponent. But if it's variable specific heat, I want VR over VR is equal to V over V. So I know the first part, right, this is kind of all background stuff. I think it'll make a little bit more sense when we start to do examples, which we will do in the next part of the lecture. Does anybody have questions before we take a break? All right, we'll come back at 7:41. All right, everybody, welcome back. So we've been talking about internal combustion engines. Hopefully, we got at least a little bit of background about how these things work, right? But now we're going to start talking about how we actually solve problems. Because when you look at a cycle and it looks like this, you can't actually solve it without a computer, right? So instead, we start to make a bunch of assumptions. Right? So we're going to neglect combustion. We're going to say that it's always a closed system. We're going to say that every process is ideal. So any process that has no heat transfer is also isentropic. We're going to say that the working fluid is only air. And we're going to say that it exists at constant specific heat. Right? And because we've made all these assumptions, right, we're stepping further and further away from reality. So we can qualitatively trust what's going on. If I change a certain variable, then how does the engine performance change? But I don't know that we can, we have less trust in the actual number, right? But that's okay, because sometimes we just want to see what changes to the engine can we make to make it run better, right? So like I said, we're going to look at different types of engines, and it's the assumption that we make while we're adding heat that defines which engine type we're looking at, right? And the first one that we're going to look at is the Otto cycle, right? So in the Otto cycle, what makes an Otto cycle is that the assumption that we make while we're adding heat, which is this process from 2 to 3, is going to be at constant volume, right? So every process is going to be ideal or reversible, right? So just like our basic version of the Rankine cycle, there are 4 different processes inside our Otto cycle. And the nice thing about Otto cycles and diesel cycles, they just are what they are. They don't get any more complicated. There's no like regenerative Otto cycle that we're going to learn about, right? So it's 4 different processes. Now the first is that compression stroke, or at least modeling the compression stroke, right? So an isentropic compression. The volume gets smaller, right? And because it's a closed system, then that means that we're putting work into the cycle, right, into the system. Our second process, what makes an Otto cycle is that we assume that the heat addition happens at constant volume. So on our PV diagram, we have a vertical line. And for these ideal gas cycles, or at least for this these internal combustion engine cycles, it's the PV diagram that I think is the more important diagram, right? Because it's a closed system. So because it's a closed system, I like drawing the PV diagram because that tells me right away this vertical line on my PV diagram, oh, there's no work associated with that process, right? Because the area under the curve is 0. 3 to 4, and that's the power stroke, the whole reason that we're doing this, right? This is the equivalent of the turbine in the Rankine cycle, right? This is our isentropic expansion. So it's expansion because the volume is getting bigger, right? Because the air at high pressure is pushing that piston down. As it does, the pressure gets lower as the volume increases, right? And then we have constant volume heat rejection or heat transfer from the air in the system to the outside world, right? That's how we're modeling that exhaust, right? So this is what an Otto cycle is, right? And you're going to have to know for all of these different cycles that we talk about, you should know what a TS diagram looks like and what a PV diagram looks like. A sample multiple choice that you won't get on the second midterm, but you could get on the final is, which of these PV diagrams is associated with an Otto cycle, right? And then you have to pick the right one, right? So you'll notice about the Otto cycle is there's only 2 volumes, right? There's the big volume, right? And there's the small volume. The volume at 1 is equal to the volume at 4, and the volume at 2 is equal to the volume at 3. Now remember, our compression ratio is always the volume at bottom dead center, the big volume, divided by the smallest volume, which is the volume at top dead center, right? So here we can have V1 over V2, or V4 over V3, or really any combination of the big volume, that's V1 or V4, divided by the small volume, which is V2 or V3. Now, I showed you a cartoon basically of how a 4-stroke engine works, but remember, this model is not exactly how reality works, right? Because it's telling us that we put work in with the compression stroke. That's real. That happens, right? But then, instead of having actual combustion, now we say, well, the piston just kind of dwells there for a little bit, and we add heat. And then eventually it goes back down and we develop work, right? And then we reject some heat, right? So I drew out this sort of like, comic strip to show you that, it's not exactly how it really happens, right? But that's okay because this is a model, right? It's sort of a cartoon representation that helps us understand how these things work, right? So in the Otto cycle, there's 4 processes, and they're the same 4 processes basically that happen in a Rankine cycle, but we have them in a different order, right? There's the compression stroke. That's where we're putting work in. That's like the pump. Then there's heat addition, right, which happens at constant volume in an Otto cycle. That's like the boiler in a Rankine cycle. Then there's the power stroke or the isentropic expansion. That's like the turbine. And then there's the heat rejection, which is like the condenser. So it's still the same basic processes, but here, instead of it being like an assembly line where each process happens in a different location, these things are all happening in the same place, right? And because it's a constant mass, we're going to use a different version of the first law. And because the fluid is different, we're going to fix the states differently too, right? So there are two processes here that we'll assume are passive, meaning that the work is 0. That's my process from 2 to 3 and from 1 to 4. They're my two processes where the entropy is changing. Right? They're also my two processes in my Otto cycle where the volume stays constant. Right? So if I want the change in U, if it's constant specific heat, then it's CV times delta T. And I can find that CV value, the specific heat at constant volume, on table A22 or A22E, depending on whether I'm using metric or English or imperial units. Right? Or I can look it up. If I'm looking it up on A22, then I'm not using this equation either. Then I'm finding the actual values for U. Right? Isentropic for air, right? Those are the processes that have no heat transfer. Right? So those are the ones where I'm putting work in or I'm getting work out. Right? And again, if it's constant specific heat, then I'm going to say delta U is CV times delta T. And if it's variable specific heat, I'm going to find the actual values for U. Right? It's important to know where the isentropic processes are. Right? And here, when I'm hunting for isentropic processes, I need to do this particularly for any cycle with air as the working fluid or some ideal gas as the working fluid. I'm looking for processes that have no heat transfer. Right? If it's a constant specific heat problem, I'm going to use the fact that it's isentropic to open up the door to one of these equations. So if it's constant specific heat, I'm looking for an equation with K in the exponent. Because it's a closed system problem, I'm going to look for the one that has a volume ratio, because these internal combustion engines, I know the compression ratio, which is a ratio of volumes. Right? So that's where I'm going to use constant specific heat. But for variable specific heat, right, I'm looking for something I can get off A22. So I'm looking for PRs and VRs. Right? But again, because I know a volume ratio here, I'm going to use VR over VR is equal to V over V. Right? Which is the same as the specific volume divided by the specific volume. But because the mass is constant, that's the same as the volume of the volume. Right? Which is my compression ratio. Or maybe the inverse of my compression ratio, depending on how I'm going through the process. So when I'm looking at these processes, the nice thing about the Otto cycle is I have only simple processes. So I'm never going to have to take the integral of PDV. Right? So I'll assume that all these things are, well, steady state. I guess it doesn't really matter because we're, what I mean by steady state is we don't, it's like you're driving down the highway on cruise control. So things like the RPM of the engine aren't changing, right? Or the power output, right? We'll say that it's a closed system. That gives us this equation. We're going to neglect kinetic and potential energies. And then each process is either adiabatic or it's passive. So if it's the compression or the power stroke, then it's adiabatic and I'm solving for work, right? If I'm adding heat or rejecting heat, then it's passive and I'm solving for heat. Because it's an internal combustion engine, I'll say all these processes are ideal. What that means is that if it's adiabatic, it's also isentropic, which lets me use those VR equations, or the equations with K in the exponent. I hope those hiccups stop. Otherwise, it's going to be an uncomfortable rest of the class for me. And after we do that, the equations we will get for the Otto cycle are, if I'm looking for the work produced in my power stroke, it's going to be the mass times U at the beginning minus U at the end. That looks, if I squint, kind of like, remember when we had power from a turbine and it was W dot is equal to M dot times H in minus H out? But because this is the closed version of the first law, we get rid of the dots, and it's not H's, it's U's, and it's not in and out, it's at the beginning and at the end. Right? If I'm looking for a heat transfer term, it's going to be mass times U at the end minus U at the beginning. Right? Compression is we're looking for work. So it's M times U at the beginning minus U at the end. Right? And if it's heat addition, it's going to be M times U at the end minus U at the beginning. But you don't have to memorize any of these equations because you know that delta E is equal to Q minus W, and you can get these equations by making some assumptions. Right? But these equations are here in the notes, and they're kind of similar to those 4-component Rankine cycle equations. But notice the state numbers are different because here we're starting our cycle where we're adding work and not where we're getting work out, which is where we start the cycle in the Rankine cycle. Now we get to the part where we say, like, oh, what's the fluid? Because I really want U values to put into my equation. Right? So there I got to know, is it variable specific heat or is it constant specific heat? Ultimately, in these problems, I'm usually going to try to find my thermal efficiency. So I need my net work and my heat in. Because the mass is the same for all of these processes, it drops out and I get an equation that's just a bunch of specific internal energies. So if I could fix all the specific internal energies in these 4 cycles, then I could find my thermal efficiency. Right? I could also model my net work as net heat, right? And then I would get this version of the equation over here. But I always think of thermal efficiency as net work over heat in instead of net heat over heat in. But it's okay to do it either way. When we fix the states, one of the things we can use is the ideal gas law, right? We can use it jumping between states like this, right? Or we can use it individually at any state, which you'll have to do if the problem asks you to find the mass. Right? Yeah, I don't know why that other slide was just randomly there in the middle. That seems like a mistake here. But so just like we can talk about our net work equaling our net work over heat in, we can also talk about net heat over heat in. And thankfully, we get the same equation, right? Because those things are the same thing, right? I don't like to memorize things, but you could memorize this equation as the thermal efficiency for Otto cycles. Personally, I wouldn't do that. I would just derive it because, well, not derive it, but get to it myself. Because on an exam, I'm probably going to ask you to do it in a step-by-step fashion so you demonstrate your understanding. But knowing what the answer looks like makes finding the path a little bit easier. Right, so we know that all of these processes are ideal, right? And the neat thing about ideal processes, we didn't really talk about this too much, but just like the integral of P, well, how do I say this? We can look at the area inside of our TS diagram, and that's going to tell us our net heat, right? Remember how work was the integral of PdV? Heat transfer is the integral of TdS. We just don't really talk about it too much. But if I look at the net heat and the net work, because there's no losses, no heat losses in an ideal process like this, the net heat and the net work are equal, right? So the area in my two curves is equal. So if I draw one diagram and I'm comparing two cycles and the area gets bigger, then I know that the net heat gets bigger, which means that the net work gets bigger, right? And the same thing is true if the area shrinks, right? So one of the cool things, even though we're using a very simple model to get to these internal combustion engine problems, right, we can look at something like the compression ratio, which tells us different volumes. And we can look at the compression ratio and how changing the compression ratio changes the performance of the engine, right? So on these TS diagrams, constant volume lines are kind of these horizontal-ish arcs, right? So if I have a small compression ratio, that's going from 1 to 2 to 3 to 4. But if I have a large compression ratio, then I get a bigger change in volume, and I go from 1 to 2 prime to 3 prime to 4. Now I can see very clearly here that increasing my compression ratio made the area inside my cycle larger, right? So as my compression ratio gets bigger, what that means is that the area on my TS diagram gets bigger, right? Which means my net heat, I have more net heat, right? Which typically means I'm burning more fuel, right? But net heat equals net work, so I'm also getting more work out, right? And it turns out that as I increase my compression ratio, the work goes up, right? And that's kind of a neat thing to know, that if you have the same or similar engines, but you increase the compression ratio, then you get more work, right? Provided you're at the same, or more power too, provided you're at the same speed. So I think that means it's time for us to go through an Otto cycle example, right? Because ultimately, that's what we're going to get tested on, is how do we do these problems. Right, so here we have an Otto cycle problem, right? And it's giving us some information, right? Like it tells us, oh, enough to fix information at state 1, some temperatures at state 3, and it asks us to find the net power in horsepower, right? It also tells us, for anytime I think power, I got to think what's going on with the stroke. So this is a 4-stroke engine. Right? And then it says, compare my answer for variable and constant specific heat. Right? So the first thing that I want to know is what contributes to net power. Right? So it's my two processes here, from 1 to 2 where I'm putting work in, and from 3 to 4 where I'm getting work out. Right? So before I get net power, I want to find net work. That's going to be the work from process 1 to 2 plus, which I expect that to be negative, plus the work from process 3 to 4, which I expect to be positive. Okay, so how do I find these things, right? So I need my first law. The first assumption that I have is that the system is closed. Because the system is closed, I know that delta E, or here, I'll even write it this way, so I don't get my deltas confused, right? So this is going to be E at the end minus E at the beginning is equal to Q from the beginning to the end minus W from the beginning to the end. Right? But here I'm also going to neglect changes in kinetic and potential. And if we want, we haven't talked about it in a while, but spring energies too, those things are all about 0. So this becomes the mass times U at the end minus U at the beginning. So for process 1 to 2, I know that, or the assumption that I'm going to make, because these are simple processes, so from 1 to 2 and 3 to 4, when I'm interested in work, heat transfer goes to 0, or heat transfer goes to 0. So that I was going to draw an arrow, but then for some reason I said not equal to, right? So that means I don't care about heat, right? So from here, I'm going to see that work from beginning to end is equal to the negative of this, which is going to be the mass times U at the beginning minus U at the end. So from 1 to 2, work from 1 to 2 is going to be the mass times U at the beginning, that's 1, minus U at the end is 2. From 2 to 3, work from 2 to 3 is going to be the mass times U, or this is 3 to 4, I'm sorry. 2 to 3 is a heat transfer process. This should be 3 to 4. So this is going to be from 3 minus U4. Right? So my net work, which is really the amount of work per cycle, and I can look here, this is in imperial units, right? So this is going to be in BTU per cycle is going to be equal to, it's the same mass everywhere, times U1 minus U2 plus U, and I expect that to be negative, remember? U3 minus U4, which I expect to be positive. Right? Again, this is going to be in BTU per cycle. But the problem actually wants this in horsepower, right? Right? Well, I guess because it doesn't want this, right? It wants, so this is like my equation 1. But what the problem wants is W dot net in horsepower. Well, that's going to be my W net, which is in BTU per cycle. Now, I got to multiply this by my cycles per minute, right? Or cycles per unit time. So for that, I need my engine speed, which is in, oops, I'll keep my color coordination here. Engine speed, which is in rotations per minute. But now, because we're in, it's a 4-stroke engine, right? Because rotations per minute is nice, except what I really care about is how many cycles per minute I have. So I know it's a 4-stroke engine, which means I got to go from bottom dead center up to top dead center, back to bottom dead center, and then over again, right? So I need 2 rotations for every cycle. So here I know that 1 cycle happens every 2 rotations. So now my cycles are going to cancel, my rotations are going to cancel, and this will give me an answer in BTU per minute, which I don't exactly want, right? Did I close it? Oh, I closed it. No, maybe I didn't. Oh, perfect. So I take out my handy dandy equation sheet and I see that 1 horsepower is 42.4 BTU per minute, right? So this answer is going to be in BTU per minute. So now I got to say that 1 over 42.4, that's 1 horsepower per BTU per minute. So I need 42.4 BTU per minute to get the horsepower. These guys are going to cancel that, and I'll get an answer in horsepower. So I have a symbolic solution. Here's the bad news. I don't think they told us the mass. Let's go back over here. They did not tell us the mass. I don't know U1, U2, U3, or U4, so I don't know W net. I do know the RPM, right? This is, I think, 2,000 RPM, right? So I need to find the mass. I need to find U1, U2, U3, or U4, at least if it's variable specific heat. And I think what I'll do is this problem, this Otto cycle problem, I'll do as variable specific heat. And then the diesel cycle problem we do next, I'll do as constant specific heat. So when it's variable specific heat, that means that delta U is equal to delta U, and I have to use A22 E to fix the states. So we're not in a terrible situation here. I know it looks bad because, mathematicians going to look at this problem and say, well, you've got 5 equations, or you got 2 equations and sort of 6 unknowns, right? But 5 of them we can find, right? So if I could fix the states, then I could get values for U1, U2, U3, and U4. In this mass, if this is an ideal gas problem and you're asked to find the mass, my first inclination is always try the ideal gas law. So let's do that first. Let's try to find the mass. So because I'm going to assume that this is an ideal gas, then I know that pressure times volume is equal to PV is equal to M times R times T. Right? Let's see what the problem tells us. It told us CP and CV. It didn't tell us R. So here I would have to get R bar. R bar is we're going to get from table or from the first page on the here. Well, I think I got the website open, so I'll show you where I would get R bar from. So here I'd go to course information, thermal reference tables. It's always going to be on this first sheet. I'm looking for R bar. I probably want it. I got 2 choices here, in foot-pounds per pound mole or in BTU per pound mole. I'm going to take this number in BTU per pound mole. I'm going to call it 2. Oops. 2 BTU per pound mole Rankine. And then this is going to be divided by the molar mass. The molar mass I'm going to find on, first I got to go through, they take all the color out. They make the English units more drab, right? Because it sucks the fun out of everything. So this is going to be 28.97. And the units on this should be something about pounds mole per pound mass, right? Or the other way around. So this is pound mass per pound mole. So when I divide these 2 things together, what's going to happen is that the pound mole in the denominator of the numerator is going to cancel the pound mole in the denominator of the denominator. And I'm going to get that R is equal to 2 divided by 28.97, 0.07. And this is going to be BTU per pound mass degree Rankine. So this is going to be true for any one of these states. So I'm looking for the state where I know the most. Usually this is going to be state 1, but let's check. So here, I'm basically, I know PV is equal to MRT, or M is equal to PV over RT. So I want to know P, V, and T. Right? Now it looks a little bit like I only have P and T. But here's the trick, is that we actually know V1, because if I look on my diagram, V1 is equal to V4. So they told me V4 down here. I'm going to see if I can grab this table. So here we know the mass. I'm going to evaluate all this at state 1 because state 1 is the one that I know the most about. The mass is going to be P1 V1 over R T1. P1 is 14.7 PSI, so pound force per inches squared. V1 is this same volume here, 0.0, I'm going to call it 2 feet cubed. I already see there's going to be unit problems, but I knew that anyway because it's an imperial problem. Divided by R, which is 0.07 BTU per pound mass Rankine. My temperature, which is already in Rankine, so they were nice to me, 540 Rankine. Right, so now I'm going to have to take this numerator. I'm going to get rid of the inches squared. So I'm going to say 12 squared inches squared per foot squared. Right, this is going to give me foot pounds, but I want BTU. So then I also have to take 1 BTU per 778 foot pounds force, right? And you can see how you can get wildly incorrect answers here if you're not multiplying by 12 squared or dividing by 778, right? Massively different answers, right? 14.7 times 0.02 times 12 squared divided by 778 divided by 0.07 divided by 540, and I got 1.44 times 10 to the negative 3. Now, when I do all of this, the BTUs cancel. The foot pounds are going to cancel with those foot pounds. The Rankines are going to cancel. So this 1 over 1 is right. So this is going to be in pounds mass. I don't know if it's the right answer, but at least I got the right units, which in a messy... This is why I don't like to use this version of the ideal gas law, because it gets annoying. Right, but now presumably we have the mass. Right? So this is good. I got the mass. Now I just got to find U. I think I'm just going to walk you through conceptually how to do this and show you on the table how I would go about doing it. But I think I'm not going to find the actual numbers unless they turn out to be really easy in terms of no interpolation, because I want to be able to get to the next topic too, right? So state 1. My favorite states are states where I know the temperature, right? So here I know the temperature at 1 is equal to 540. This is great because this means I can go directly to A22, in this case E, and find U1. So this is 540 Rankine. So now I'm going to jump down to the table here, which I hope is down here. Yeah, good. 540, right? So now here I'm going to get U1, but I'm also going to get VR1. Right? I'll put these numbers in the chat. So this is 92.04 and 144.32. So U1 is going to be 92.04. This is BTU per pound mass. But VR4 I'm going to need, or VR1 I'm also going to need, right? And it's 144.32. Has no units. Okay, so now why did I do that? It's because as I go from state 1 to state 2, I got to think about this process. Anytime I have a cycle that uses ideal gas, I say, is it delta S equal to 0? And as I move from state 1 to state 2, the answer is yes. Oh, it really doesn't like... need a better video card. Right? So here, as I go from 1 to 2, if I look here, right, oh, this is a process with no heat transfer, which means it's isentropic. So because that's true, now I can use my delta S is equal to 0 equations, but because it's variable specific heat, I'm not looking for one with K in the exponent. Instead, I'm looking for one that's going to be, so this is going to be VR2 over VR1 is equal to either little v2 over little v1 or big V2 over big V1, right? Now, when I think about this, so this is going to be, if I drew my PV diagram, this is state 1, 2, 3, 4. So this is going to be my little volume over my big volume, right? So this is 1 over R. Right? In this problem, they told me that V1 over V2 is 10, but now this is V2 over V1, so that's 1 over 10, or little VR2 is equal to VR1 over 10, which is going to be 14.432. Right, so what do I do with this information? Right, I got to go to A22E. So before, when we were on A22E, we knew, so for state 1, I knew T1, and I used that to get VR1. But now for state 2, I'm going to know VR2, and I'm going to use that. I guess over here, too, we picked up U1. And I'm going to use this to get U2. Right, so 14.43. So I'm looking for a VR value that's around 14.43. So it's in between these two. I could do some interpolation if I wanted to, but just for the sake of doing it quickly, let's pretend that it was 14.25. Right? So because if it was 14.25, then I would have to go over here and I would get U. Right? Really what I'd have to do is find some interpolation factor A. Right? And I'd have to interpolate over here, and then I'd interpolate in there too. But just for the sake of doing it quick, let's say that because VR2 was equal to, or approximately equal to 14.25, then U2 is approximately equal to 231.63. Just to quickly check, we think that this is putting power in, or putting work into the system. So if I take the mass times U1 minus U2, I should get a negative number, right? And 92 minus 231 will give me a negative number. So I don't know if it's the right answer, but the sign's right, right? So I can't prove that I'm wrong. So this is good. We've got U1 and U2. Now, the nice thing about U3, and this will often happen in these problems, is that, here it's a little tricky. Usually, state 3, I was going to say, often they'll just give you the temperature here, right? But they didn't give us the temperature. So now I've got to go from state 2 down to state 3. And I ask, is delta S equal to 0? The answer here is no, because 2 to 3 is a heat transfer process, right? So I can't use my VR equations here. So I'm kind of stuck, right? Except it's still an ideal gas law problem, right? So I could say that I'm going from state 2 to state 3, so P2 V2 over T2 is equal to mR, right? But the mass is constant, and it's always the same gas, so the gas constant is the same. So that's going to be P2 V or P3 V3 over T3, right? And what do I know about my process from state 2 to state 3? This is my heat addition process, which happens at constant volume. So I know here that V2 is equal to V3. So if I'm trying to find T3, which would be good because then I could find U3, this is going to be equal to T2 times, where are we? So T3 comes up here, T2 comes up there, and this is going to be P3 over P2. So do I have that information? So I do have P3 and P2. Right? So in this case, now that I went back to here, right? Remember, I only got U2 from here. It turns out that I actually needed T2 as well. So T2 is going to be approximately equal to, I'll go back to that line down here. So T2 is going to be about 1320. So T3 is approximately equal to 1320 degrees Rankine. Now the beauty of doing the problem like this is as long as my pressures are in the same units, I don't have to do any unit conversion. All right, so this is going to be 1080 divided by 14.7. 80 divided by 14.7 times 1320. That seems too high. The number that I got here is, did I mess up the ratio here? The number that 1080 divided by 14.7 times 1320. Yeah, I'm getting like 9,700 Rankine, which seems too high to me. So what did I do wrong? Oh, yeah, thank you. P1 is not P2. So now I got to go back to this equation, right, and also use this, right? So now I can say that P1 V1 over T1 is equal to P2 V2 over T2, right? And I can get that P2 is equal to P1 times V1 over V2 times T2 over T1. V1 over V2 is 10, right? V1 over V2. So this is 10. T2 over T1 is 1320 divided by, did they give us T1? I think they did. 540. P1 was 14.7. This is going to be a better number. So this is going to be 14.7 times 10 times 1320 divided by 540. So P2 is 359.3. This is in the same units as P1, which is PSI. And now when I put that into here, this should be 359.3. 1080 divided by 359.3 times 1320 equal to 3967.7. Which unfortunately is too high for the table, so we can't find it on this table. So this would be a problem where we'd want to then revert to doing it as constant specific heat. But let's say that we could find this, right? So if this was T3, then what we would do is we would go to table A22E, and now this becomes just like state 1. So because if this was A22E, we know T1 or T3 now. So we're going to use that to find U3, and we're going to use that to find VR3. Now, as I move from state 3 to state 4, again, I ask, is delta S equal to 0? And this time, the answer is yes. Because this is just like from state 1 to state 2, right? 1 to 2 was isentropic, 3 to 4 is also isentropic. So now this means that I can use my isentropic equations because it's variable specific heat. Then I'm going to say VR4, because that's the one I'm trying to find, over VR3 is equal to V4 over V3. But now I go back and I look at to try to find V4 and V3, right? V4 is my small volume. V3 is my big volume. Right? So 4 is the small, no, 4 is the big volume, I'm sorry. So 4 over 3 should be the same as 1 over 2, which is 10. So this is going to be R. So now from here, VR4 would be equal to 10 times VR3. And then I would go to my table A22E, and now this would be like state 2, because here I'm going to find VR4 and then work to the left and find U4. Right, so I know we kind of reverted to the process because we didn't have the number for U3. But hopefully understanding the process helps. And now we would go back to our sort of initial equations. And we'd say, yes, I found the mass from the ideal gas law. I found U1, U2, U3, and U4. That means I know W net. So then I can put it into this equation, and I can get an expression for horsepower. Now, if the only difference, the difference is if this was constant specific heat, then the delta U's would become CV times delta T. And instead of using VR over VR is equal to V over V, I'd use some expression where T over T was equal to V over V to the K minus 1 if delta S was equal to 0. So it's still similar. We're still going through the same processes. Anytime you're using the ideal gas law, you're still going to use the ideal gas law. It's just that when it's constant specific heat, you don't have to find the specific internal energies. You're only looking for the temperatures. And once you know the temperatures, then you can go back and solve the first law. So hopefully that kind of makes sense. The nice thing about these Otto cycle problems is they tend to mostly be kind of the same. Because unlike something like a Rankine cycle problem, where I can give you almost infinite complexity, there's not too much I can do to spice up an Otto cycle problem, right? All I can really change is the inputs that you're given and the outputs that I want, right? I can't make the cycle more complicated. So usually we'll follow these same steps when you go through and fix the states. A lot of times that's kind of the hard part, where you know the original temperature, that gives you U1. Then from 1 to 2, it's isentropic, so you use the isentropic relationship. From 2 to 3, you can only use the ideal gas law, but then from 3 to 4, you can use the isentropic relationship again. Does anybody have any questions? All right, let's take our last break here, and then we'll go over diesel cycle problems, and from there, we'll do an example. So we'll come back at 8:40. All right, welcome back, everybody. One last topic for tonight. We talked about Otto cycles, right? Now, the difference between the Otto cycle and the diesel cycle is the assumption that we make when we're adding heat. Otto cycles add heat at constant volume. So as I move between state 2 and state 3, this volume stays the same. But a diesel cycle is going to switch that up a little bit by assuming that it's the pressure that stays constant as I'm adding heat and not the volume. Right? So these diesel cycle analyses are a little bit more complicated than Otto cycles. So in the diesel cycle, what makes the diesel cycle a diesel cycle is that we assume that heat addition happens at constant pressure. Right? So my PV diagram looks kind of the same, except as I move from 2 to 3, it's no longer a vertical line. Now it's a horizontal line. Right? Maybe you've got alarm bells going off because of that. But if not, we'll see that you will in a second. Right? So it's still, the first process is still an isentropic compression. There's work happening, but there's no heat transfer. Then this 2 to 3 is constant pressure heat addition. So heat's being added, but it's happening at constant pressure. Now this is a horizontal line, which unfortunately means that the work is not zero as we add heat. Then as we move from 3 to 4, it's an isentropic expansion. Now again, it's like the Otto cycle was. And even though we add heat at constant volume or at constant pressure, we assume that we remove heat at constant volume. So that's like the Otto cycle too. So there's one process that's different here, but it's kind of an important one, right? And we'll see that it messes things up a little bit because I've got work going in at state 2, or at state from the process 1 to 2. But then the process 2 to 3, not only am I adding heat, but I'm getting work out because my volume is expanding, right? Remember, anytime the volume gets bigger, then work is positive. I have constant volume or isentropic expansion, so the volume is increasing, so there's work but no heat transfer. And then I have heat rejection from state 4 to state 1. And we'll see that the fact that this is no longer a simple process from 2 to 3, that's what makes diesel cycles harder or more complicated than Otto cycles. Right? Because this is a horizontal line as we move from 2 to 3. Sometimes people will talk about diesel cycles having a 2-stage power stroke, because we're getting work out for 2 of these processes. As we're adding heat, we get work out, but then even after we stop adding heat, we get work out again. So if I try to find the heat out, this is the same analysis we would do for an Otto cycle, right? Delta E is Q minus W, right? But I make some assumptions, so it's delta U is equal to Q minus W, but there is no work here. So this one's pretty straightforward, that Q from 4 to 1, as I'm rejecting, is U at the end minus U at the beginning. Right? But what if I wanted the net heat? If I want the net heat, then I have to find the heat in, right? And this is the tricky part. Now, this looks like a first law problem I might have asked you on the first midterm, because I have this constant pressure process. There's heat and there's work. So I have to find the work separately, which means I need some pressure-volume relationship. Thankfully here it's nothing too exotic. The pressure is constant, so I pull that out of the integral, and then I have P times the integral of dV, or pressure times the change in the specific volume, will give me the work over the mass, or just the work is pressure times the change in volume. So now if I want Q from 2 to 3, I would have to sub this in for the work, right? So what I did here was I'm trying to isolate for Q 2 to 3. So I have U3 minus U2, but then I got to bring the work over here. So this becomes plus P2 times V3 minus V2, right? But that P2 is the same thing as P3, right? So I can multiply that pressure by V3 and call it P3, and I can multiply that pressure by V2 and call it P2, right? So I could group these terms together, not by whether they're U or whether they're PV, but by their state number. When I do that, I get U3 plus P3V3 minus, in parentheses, U2 plus P2V2. Now remember, we had something similar when we derived the equation for the first law in open systems, right? And this was like the reason that we said, like, well, why don't we just call that thing specific enthalpy, right? So it's a little weird because it's a closed system. But here, this heat transfer per unit mass is equal to H3 minus H2. So in the diesel cycle, heat in looks almost like heat in for the Otto cycle, but in the Otto cycle, it was U3 minus U2. Now, you always want to be able to demonstrate that you can get to this answer. But kind of a funny way that I remember it is the equations are actually almost always the same between Otto and diesel. But in diesel, the two states that touch the horizontal line, instead of specific internal energies, they become specific enthalpies, right? The letter we use for specific enthalpy is H, so the two states that are on the horizontal line become H's instead of U's, right? I remember that because horizontal starts with H. But you don't need to remember it because you can just get it from the first law, right? And we're just using H because it's a mathematical convenience here. It's not an indication that this is now an open system, right? The system is still closed. So now, what if I was trying to find the net work, right? Now I have 3 terms that I have to figure out. This work from 2 to 3 was the integral of PdV, but we already calculated that, right? That's that constant pressure times V3 minus V2. The work from 3 to 4, which is the other positive term, if I use the first law here, right? There's no heat transfer in this particular process. So work is just U at the beginning minus U at the end. Work that goes in, this is negative, but I still add it to let the first law take care of the signs. Right? Again, I cancel Q, and I get work is U at the beginning, U1, minus U at the end, U2. Just like I did for net heat, I'm going to collect the terms, or heat from 2 to 3, I'm going to collect the terms by their state number, not whether it's a U or a PV. And I'm going to get that my net heat is H3 minus H2 plus U1 minus U4. Again, this is almost the same answer that we got for the net work for the Otto cycle, but the Otto cycle was U3 minus U2 plus U1 minus U4. Right? So those two states, state 3 and state 2, that are on the horizontal line, they become specific enthalpies, or H's. Right? You might also notice H3 minus H2 is Q in, and U1 minus U4 is Q out. So this is Q in minus Q in plus Q out, but Q out is negative, which is what it's supposed to be, right? Because the net work is the net heat, right? So that hopefully makes sense. Right? If we're trying to get a thermal efficiency, now we've got equations for net work and net heat and heat in. Right? So I can sub that in. And again, I'm going to get equations that end up looking just like the Otto cycle equations, except those two states that are on the horizontal line become specific enthalpies. Right? So again, you don't have to memorize these final equations, because I'm probably going to ask you separately to work them all out. Right? But it's always nice to know what the shape of the equation should look like when you're trying to work it out. Right? Now, when we look at a diesel cycle PV diagram, it's a little more complicated than an Otto cycle PV diagram. The Otto cycle, remember, because the heat addition happened at constant volume, there was only two volumes in the process, in the whole cycle, right? There was the big volume and the little volume. But now, there's the big volume, the little volume, and the in-between volume, right? So instead of just one volume ratio, we're going to have two volume ratios here. Now, the first volume ratio is the same. It's the compression ratio. The biggest volume in the cycle divided by the smallest volume in the cycle. You should always get a number bigger than 1. Right? As we increase the compression ratio, R, then what happens is we increase the efficiency. I have never used this equation, but it's in the textbook. Right? You can also get efficiency from that equation if you want. What you'd see here is if RC, which we're going to talk about next, stayed constant. K, remember, is CP over CV, so that's just a function of what gas you're using. Right? And here, if R gets bigger, K is usually 1.4 for air. Right? As R gets bigger, this 1 divided by something, that gets bigger. So this negative term gets smaller as R gets bigger. So as compression ratio increases, efficiency gets closer to 1. Cutoff ratio. So this is kind of some measure of maybe how quickly we're burning the fuel inside the diesel engine. Right? It's the volume. It's always the bigger one over the smaller one. Right? And the cutoff ratio is talking about the heat addition process. So it's the bigger volume in the heat addition process divided by the smaller volume in the heat addition process. Now, what this equation that I never used before, didn't put on my equation sheet, is telling me is that as the cutoff ratio gets bigger, my efficiency decreases. That's telling me, like, I want to burn my fuel faster, basically. The faster you burn your fuel, the more efficient your engine gets, right? Which kind of makes sense, because then because the faster you burn your fuel, the faster you get this pressure the force that's pushing the piston down, right? You get more like an impulse, right, as opposed to like a slow burn, right? So you want to burn it fast, and then you get better efficiency. At least that's how I think about it, right? But the equation tells us as the cutoff ratio gets bigger, as it takes you longer to burn the fuel, your efficiency gets worse, right? You could work that out because in the top, it scales by the cutoff ratio to the power of k, and k is bigger than 1. On the bottom, it squares to the cutoff. It scales to the cutoff ratio. So here, this term, which is in the negative part, gets bigger if everything else stays the same, except the cutoff ratio gets bigger. So now we're going to do a diesel cycle problem. Now, there's some magic that happens in the diesel cycle problems, which you'll get to see as we fix the states. So the diesel cycle problems are a little trickier. I'm going to do this one with constant specific heat. So here we have this diesel cycle problem, and it asks us a couple of things. Right? It wants us to find the heat in, the thermal efficiency, and the cutoff ratio. So the first thing I always want to do is get symbolic solutions. Right? So here it wants Q in, it wants B was thermal efficiency, C was the cutoff ratio. Cutoff ratio, I just know by definition, right? It's going to be the volume. So this is the heat addition process. It's V3 over V2. The big volume in the heat addition process divided by the small volume. So this is V3 over V2. So that one I know. But let's go through the other ones separately. Right? We did this a little bit already in the slides, but I'll do it by hand here too. So Q in, this is for, I can get this from the first law, from state 2 to 3, which is my heat addition process. I'm going to assume that the change in the kinetic energy is approximately equal to 0, which is approximately equal to the change in the potential energy. Here, what I'm going to get is the mass times specific internal energy at 3 minus specific internal energy at 2 is equal to Q 2 to 3 minus W 2 to 3, or that Q 2 to 3 is equal to M U3 minus U2 plus W from 2 to 3. Remember, my diesel cycle, PV, starts here at state 1, goes up to state 2, is flat for, so I'm talking about this process here from 2 to 3. I can't, unlike all the other processes and all the other internal combustion engines, right, I need an expression, right? This is work is equal to the integral of P dV, and I know that pressure is constant as I move from state 2 to state 3. Right, so I'm going to call this equation 1. My work from 2 to 3 is equal to the integral P dV, but P is constant. So this is going to be P, I'm going to call it 2 for now, times the integral from 2 to 3 dV. This is going to be pressure times V3, P2, times V3 minus V2. I could also pull the mass out, P2, little v3 minus little v2 times the mass. This is my work. Into 1. Then Q from 2 to 3 is going to be equal to the mass. Mass also factors into this work term, so I'm going to pull it out of all of these things. So U3 minus U2 plus, this is going to be, P2 is equal to P3, right? So when I multiply this pressure times this term, I'm going to call it P3, and I'm going to call it P2 when I multiply it times that term. So this is going to be P3 V3 minus P2 V2. Or mass times U3 plus P3 V3 minus U2 plus P2 V2. Or Q2 to 3 is equal to the mass times H3 minus H2. A little bracket happy on this one, but now we have a symbolic solution for Q2 to 3. Does that make sense? The next symbolic solution we want is the thermal efficiency. This is part B. The thermal efficiency is going to be W net over Q in. W net is going to be W from 1 to 2 plus W from 2 to 3 plus W from 3 to 4 over Q in, which is Q2 to 3. Okay, so I already know W2 to 3, right? This is mass times, let's go back to make sure that I don't mess up the sign here. But I know that the work is the mass times P3V3 minus P2V2. P3V3 minus P2V2. So I have one of these three terms already. For 1 to 2 and 3 to 4, I know that Q is equal to 0. So when I do my first law, I'm still going to assume that there's no kinetic and potential energy changes. So this is going to be mass times U at the end minus U at the beginning is equal to Q minus W, but Q is equal to 0. So work is going to be mass times U at the beginning minus U at the end. Right? So work from 1 to 2 is mass times U1 minus U2. And work from 3 to 4 is the mass times U3 minus U4. I know I did that quick. Does it make sense? So now I'm going to put this, and this into my thermal efficiency equation. So thermal efficiency is equal to, on the top, mass times everything, U1 minus U2 plus P3 V3 minus P2 V2 plus U3 minus U4, right? All divided by my heat transfer in, which is mass times H3 minus H2. I don't care what the mass is here because it drops out. But again, I can group in the numerators. I can say U1 minus U2, this is minus U2 and minus P2 V2. So this becomes P2 V2 plus U3 plus P3 V3 minus U4. Oops. All divided by H3 minus H2. So this is going to be U1 minus H2 plus H3 minus U2 or this is U4, sorry, divided by H3 minus H2. If I wanted to, I could rewrite this as 1, right? Because this part is the same as the denominator. And this would be plus U1 minus U4 over H3 minus H2. You can do it that way if you want, or you don't have to. So these would be my expressions if I was doing it as variable specific heat. But last one we did is variable specific heat. So let's assume constant specific heat. That's going to change this to 1 plus, this is delta U, so this is going to be CV T1 minus T4 divided by CP T3 minus T2. So you got to be careful which one is a CP and which one is a CV. This one becomes MCP because it's delta H T3 minus T2. And my expression for the cutoff ratio doesn't change because it's just volumes. It's got nothing to do with delta U. So, did they tell me the mass in this one? Let's see. They do. The mass is constant, so they told me the mass. That's nice. So I know the mass. I don't know V3 or V2 because I don't think I know either of these volumes. Right? But I know the compression ratio. I don't know, do I know T3 or T2? Which temperatures do I know? I know T1 and T3. So I know T3, that's good. I don't know T2. I think they gave me CP. They gave me the mass. I think CP and CV they gave me, and I know 1 and 3, but I don't know 2 and 4. So that's the symbolic part. Now comes the how do we fix the states part. When I'm fixing states in constant specific heat, really what I want to know is I want to know the temperature and the pressure at all states. Let's bring down the state table so that I'm not jumping back and forth too much. So at state 1, we know the temperature. Do we know the pressure? We know the pressure. We don't know the volume, but we do know V1 over V2. Hopefully that's enough. Now I'm going to move between state 1 and state 2. I ask myself, is this process isentropic? I'm going to ask myself that question every single time I have a cycle where the working fluid is air. So as I go from 1 to 2, there's only work happening, which means that it's isentropic. As I go from 2 to 3, there's work and heat. So this is delta S is equal to 0. 2 to 3, delta S is not equal to 0. Anytime there's heat transfer, it's not isentropic. Delta S is equal to 0 as I go from 3 to 4. And here I'm rejecting heat. Delta S is not equal to 0. So as I go from 1 to 2, I can use an isentropic relationship. I love it when I can use isentropic relationships because those are the key to finding how to fix these, how to fix the states when the working fluid is air. I need to know where my isentropic relationships are. Now I'm just trying to find my equation sheet again, right? So ideal gas, yep. Isentropic, yep. But is it constant or variable specific heat? When it was variable specific heat, I'm looking for VRs or PRs. But now because it's constant specific heat, I'm looking for something with K in the exponent. And because I know the volume ratios, I'm looking for this one. So T2 over T1 is equal to, this is a little tricky because it's inverted, V1 over V2 to the power of K minus 1. So here, T2 over T1 is equal to V2 over V1 to the power of K minus 1. No, V1 over V2 because that's inverted. See, I just told you, be careful for that, right? Because maybe because it's a thing that I mess up sometimes. Right? So usually if 2's on top here, 2's on top here, right? But the thing is you got the equation sheet, so use the equation sheet. Right? So now, K is equal to Cp over Cv. For air, this is usually 1.4. I don't know if it's given. If it's not given, I think maybe it's table 820 or something where you look it up. But here they gave me Cp and Cv, so I can just divide them. Or you'll find that it's usually about 1.4. It'll change a little bit depending on the temperature that you look it up in. But this is R, right? 17. So here, I know that T2 is equal to T1 times 17. Well, let's leave it symbolically for a second. V1 over V2 is R to the power of K minus 1. Or, I see here they told me T1 was 520. And they were nice because they gave it to me in Rankine. This won't work if you use Fahrenheit. R is 17 to the power of 1.4 minus 1. 17 to the power of 0.4 times 520 is equal to 1,615, well, 0.04 Rankine. Temperatures are good because temperatures are what I need to do the first law, right? Because remember, I'm either going to have a CV or a CP times delta T. It's usually not enough, though. But let's say I did think it was enough. Because in my final equations, right, in the symbolic solutions I have, I'm only going to have a T2, right? So I think I don't need P2 based just on those equations. So now, as I go from state 2 to state 3, I ask, is delta S equal to 0? From 2 to 3, this is Q in and work out. So delta S is not equal to 0. It means I can't use some expression that has K in the exponent. But I can still use the ideal gas law. I could also still use the first law. I already did that to find things like Q 2 to 3 and W 2 to 3, right? The ideal gas law tells me P2 V2 over T2 is equal to mR, but it's a closed system, so mass is constant. And we assume that there are no chemical reactions, so R is constant, the gas doesn't change. So this becomes P3 V3 over T3. And you know what the cool thing is? This is a diesel cycle, which means constant pressure from 2 to 3 as we add heat. So P2 is equal to P3. So here I didn't know P2, but I didn't necessarily need to, right? Because it just cancels out here. So here what I find is I'm looking for T3, and it's going to be T2 times V3 over V2. But the thing is, I know T3 already, right? T3 was given, and then you might say, well, why did I even do this? Because they told me T3. But there's still a reason we did this, right? So T3 was known, so I'm not going to use this in this question to find T3. Right? But I didn't know what V3 over V2 was, right? This is my cutoff ratio. So anytime you have a diesel problem, if you're trying to find V3 over V2, you know that it's going to be T3 over T2. So here, once I found T2, I think that this was T3 4,000. I know I just looked. 4,000. So this is going to be 4,000 divided by 1615.04. Right? They're both in Rankine. So this is 4,000 divided by 1615.04. And that's going to be 2.4. Well, we'll say 48. That's my answer to part C. I wasn't even trying to get it, right? I was just moving through my states. So this is the thing, when you're trying to find the cutoff ratio, you want to use the ideal gas law from state 2 to state 3. Right? Or you just remember that the volume ratio happens to be the same as the temperature ratio as you're adding heat here, because it's happening at constant pressure. Now, I know we're getting late here, but you want to pay attention for this next part, because if people mess up diesel cycle problems, it's because they have a problem going from state 3 to state 4. So from 3 to 4, air is still the working fluid, so I ask, is delta S equal to 0? The answer is yes. The nice thing about these diesel cycle problems is they'll usually give you 2 of the temperatures right off the bat, right? Or I guess they could give you a temperature and maybe a compression ratio or a cutoff ratio from 2 to 3 or something, and then you could find the other temperature. But getting T4 is tricky, right? So again, because this is true, I have 2 choices. I can use some equation that's VR over VR, but I'm not going to do that because that's variable specific heat. Or I get some equation that's temperature over temperature is equal to volume over volume to the K minus 1. Right? In this case, I'm trying to find T4, right? And I'm moving from T3 because 3 to 4 is isentropic. So this becomes V3 over V4. The problem is I don't know V3 over V4. And I don't think there's a way for me to calculate it. You know, it's funny because I know the ratio of V1 to V2, and I know the ratio of V3 to V4 or V2 to V3. So if I knew like one of those volumes, I could calculate the rest. Like if it gave me the diameter or something, right? But they didn't. So this is what I have to do, right? I got to play around with this volume ratio, right? So we have V3 over V4. And it's helpful here to know how to draw a PV diagram, state 1 to state 2 to state 3 down here to state 4. So I know that V1 and V4 are the same thing, right? So this is the same as V3 over V1 because as I move from here to here, V4 is equal to V1. That part makes sense? This is the part that doesn't make as much sense. I'm going to take this and I'm going to multiply it by 1. I can do that, right? I'll get the same answer. But I'm going to multiply it by a very special one. V3 over V1 multiplied by V2 over V2. This is kind of the sleight of hand that happens in the diesel problem. There are a couple of things that people often mess up on these problems. Some of them are sort of consistent with all the air problems, like they didn't put the temperature in Rankine, right? Or they, they couldn't find the right isentropic relationship. But this is something people forget all the time how to do. This ratio, and it's going to happen in this case too, because if it's VR, that other equation, if this was variable specific heat, then this would be VR1 or VR3 over VR4 is equal to V3 over V4. So instead of having, you'd still have to find V3 over V4, right? Now, here's where it gets interesting, right? I'm going to move this around now. So this becomes V3 over V2 multiplied by V2 over V1. None of that's cheating in math, right? I multiply by 1, and then I use the fact that the order of operations doesn't matter where I put the multiplied parts by, right? 1 times 2 is the same as 2 times 1, right? I forget if that's commutative or whatever, right? There's a special math word for that. Now, V3 over V2 is my cutoff ratio. V1 divided by V2 is R, right? So V2 over V1, this is 1 over R. So this means that this is equal to RC over R. You see how that happened? So there's 2 things that we needed to know here. That V4 was equal to V1, and then I multiply the whole thing by 1, but the one that I multiply by is V2 over V2. And that means I can change V3 over V4 to RC over R. Right? So now T4 over T3 is equal to RC over R to the power of K minus 1. Or T4, which is what I'd really like to find, is equal to T3 times RC was something like 2.5, I think. 2.48 divided by 17. K is 1.4. So this is all to the power of 0.4. 2.48 divided by 17, all to the power of 0.4 times T3, I think was 4,000. Yep. And that's going to be equal to 1852.1 Rankine. So now, if you want the numerical answers to all these things, you can go through and look at them, right? But now, when I look at my symbolic solutions here, I knew CP and CV. Now I know T4 and T2. Right? And then when I look over here, I knew T3 and T2. Right? And I found RC by going through and fixing the states, running the ideal gas law between state 2 and state 3. So that's generally how we do diesel cycle problems. In a way, it's nice because there's only 4 states. And usually they'll give me 2 of the temperatures, or they have to tell me the cutoff ratio. Things that are tricky here is I got to remember, as I go from 1 to 2, delta S is equal to 0. As I go from 3 to 4, delta S is equal to 0. Here, I got to use the ideal gas law. RC is equal to the temperature over the temperature, right? So T3 over T2. And over here, I got to remember that V3 over V4 is the same thing as V3 over V2 times V2 over V1, which is equal to RC over R. Right? So diesel's definitely trickier. It's trickier because as I go from 2 to 3, then there's heat and there's work. Right? So that means I'm going to get H2s and H3s, right? But still U1s and U4s. So the first law stuff is tougher, and the state fixing is a little tougher too. So diesel is the harder of the 2 problems, but I think once you do a couple of these, just like the 4-component Rankine cycle, there's not too much you can do to change these problems around because they're all mostly the same. So we got an extra 15 minutes or so if anybody has any questions. And if not, you can just go to sleep 15 minutes earlier. Not that you sleep though, right? Because you're young. This is tough for me because I'm usually in bed by 9:30. So it's like, you know, I'm usually up by I'm up till 11 usually now on Tuesdays. Totally screwing up my whole sleep schedule here. But I'm an old man now, so that's how it goes. At dinner first, yeah. I usually try to eat before 9 o'clock as well. So, again, this is what happens when you're an old man. Or an old woman, probably, too. Anyway, I hope that everybody has a great night. And I hope you have a great weekend. And I will see you on, well, tomorrow if you come to office hours. I think that I unfortunately will end up, well, I won't be around on Monday for office hours, so I'll move my office hours to Wednesday at the same time because I won't be around. But I do know that at least one person is traveling on Wednesday, so if you want to set up an extra time for an office hour before your alternate exam time, let me know and we'll set something up. Okay? Thanks, everybody.
Thanks so much. Have a good night.
No problem, you too.
Thanks so much. Have a good night.